Anthony Azema, and here's my lab 2 about the motion of a falling object. So let's get right into it. And you see on this first slide is a little Newton looking at his apple falling. Man, oh man, do I love gravity. Okay. So let's talk about the lab. So in this lab, we will analyze an object that is thrown and moves like a projectile. And the observed motion will then be compared with two different computational models. One computational model that takes into account drag force and the other one that totally disregards it. So the reason why we're doing this, the whole purpose of this is to showcase Newton's second law and how drag force may impact an object and have an effect on the results. Okay, so let's talk about the system and the surroundings. So the system is the object, our balled up paper ball, and our surroundings, air, our hand when we're dropping the ball, and earth, gravity. Gotta love gravity, like I said before. So let's talk about the observed position. The observed position is viewed via tracker, while the predicted position will be seen via glow script. And the entire outcome is to model the model. What we think is going to happen is that the model takes into account drag force, and that will resemble the model that we get from the tracker data. So let's see if that happens. Okay, let's talk about the fundamental principles that we're using in this lab first. So we have Newton's second law, we have gravitational force and drag force. Let's talk about Newton's second law. So looking at Newton's second law, that is the acceleration of an object and the net force acting on this said object and how they are directly proportional to each other. So we see this in this equation over here, and in this little diagram I tried to draw showing that we have gravity working downwards on the object. And then the drag is working upwards on this ball. And then the net force, it's also pushing downwards, which would then lead to a change in momentum. So Newton's second law, it's all about change in momentum and the net force acting on our system. Let's talk about gravitational force. Guys, we are on Earth, so that means that gravity is a big deal. And so that's the force that's going to be pulling down on this ball as it falls. And then we're looking at drag force. With drag force, when the ball is at rest, then the drag force, oh, when the ball has not moved, the drag force is at rest. There's none of it. No, the ball is at rest. There is no drag force when the ball is at rest. And then as the ball falls, the drag force increases, and then boom, we reach this terminal velocity, and then the velocity interacts with the gravitational force, and then boom, the ball is on the ground. So look at this video. My little brother was able to help me out with this, and boom, the ball hit the ground. And these are my results over here. We found the change in time. We got the 0.698 over here that I'm going to use in my while loop in my code, and then also here we got our vector from the results. So this is amazing stuff. Okay, boom, here's my code. So, I edited the lines that were needed to be edited so that everything worked out. And then boom, we have our equations over here. Um, let's see. Oh yeah, so the equations that we have over here are the position update formula and the velocity update formula so that the graph needs to graph what so that the graph graphs what it needs to graph. So let's see. And is like constantly updating the position and the velocity if we're to talk about it scientifically. So let's look at this model. So boom, when there was no drag, we see that the lines look a little bit different than if there was drag, and if yeah, it's different than if there was drag. And if you look at the drag model and tracker, they start to align. And this is actually exactly what we predicted because drag takes into account forces that no drag did not. So let's talk about it. Let's see some possible errors in my experiment. So I said let's talk about it. Basically, the reason why that is because drag takes into account um, the different velocity and everything. So that's why it's going to align more with the tracker, which is more accurate. Possible errors. So let's look at an environment. So when my brother dropped the paper ball, the fan was on in the room. So that definitely affected it. Tracker, sometimes it's hard to actually track the points, like using the model and, tapping, tap, 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 so that you can get each position as it falls. And then the ball itself, it was not like fully circular. So maybe different forces were acting on different parts of the ball because the ball was unevenly circular. But then also, even the way the video was recorded, it could have been tilted a bit. So that's another possible error. So let's talk about our further discussion here. So in the model, which model predicts terminal velocity? So the one that predicts terminal velocity is going to be the gravity and drag model, and that showed us a lot. In the model, that only has gravity results in velocity increasing at a constant rate. However, when drag is included, velocity increases more slowly and eventually levels off, showing that the presence of a terminal velocity. Let's talk about the next question. What would happen to terminal velocity if the object was initially thrown straight up? Nothing much would change other than the fact that the faster reach conclusion would have occurred for the object's velocity. Okay, thank you so much for watching. I hope you have an amazing day. Thank you so much. Rock on.